All right, so a couple warm-up problems. We've got a lot of series tests. We're about done with our series tests. We've got a couple more this week, and then we're done with our full library of tools or attack methods that we can try to find series divergence or convergence. So this first one, what'd you guys try?
Alternating series.
Okay, so it's a classic alternating series, so your first instinct is probably, well, obviously it's got an alternator, right? Not like an alternator from your car. This is what I'd call an alternator in mathematics. So this clearly has an alternator, so that's your instinct probably to apply it. Did it work? Did it meet the conditions and converge?
Yeah.
I don't think so. The first condition is you've got a what?
The limit.
The limit has to be 0. That's a pretty common type of condition we've seen with lots of different tests, right? So the limit has to be 0, but it's not. The limit of the non-alternating part is what?
3/4.
Right, so I'll just write it out. So that means the alternating series test fails. You can't conclude anything with it. So, what then?
Try something else.
It could converge, but the divergence test, what does the divergence test say?
If the limit is n equals infinity does not equal 0, then it diverges.
Yeah. So if you stick the whole thing in there, alternator and all, what's that?
Plus or minus.
No.
It doesn't equal. That's not 0 though, so it diverges.
Divergence test succeeded. This diverges by that. So I'd say, therefore, that thing diverges by the divergence test. Done. Okay? Good. This one. Classically alternating again. Can we use the alternating series test on it? A divergence test, if we think about it like number 1, is going to fail, right? Because the limit goes to 0, clearly. So no information from the divergence test. But alternating series, I think the limit goes to 0, doesn't it? The limit of the non-alternating part, a sub n, that's 0. I mean, we don't even really need to say anything about it. By order of magnitude, you can use L'Hopital a few times, whatever. I'm just going to say it's 0 done, okay? Is it decreasing? Remember, we can do that with 2 ways. We can look at a sub n plus 1, the next term compared to the previous term, and see if it's less. Or we can take a derivative. I'm going to do it with a derivative this time because it's been a while. We need to do practice on derivatives. So help me with the derivative. Let's find the derivative of, let's say f of x is this, right? So what's f prime?
So x cubed plus 1 times 2x minus x squared times 2x squared all over x to the 3rd squared.
Very good. You guys remember? Nice work. Okay, let's consolidate and see if anything drops out. Hopefully it will. All right, so we're going to have
X to the 4th
2x to the 4th plus 2x.
minus x to the 3x.
Like terms. 2 minus 3 is negative 1. So that factors, because I need to see if the top is negative, right? Because the bottom is clearly positive, so the top better be negative, or we're not decreasing. My voice is just so lovely. Let's see, x negative x cubed plus 2. The bottom is kind of irrelevant. Is that going to be negative? Now remember, it doesn't have to be negative for all integers. It just has to be negative for where x is. Really, it doesn't even have to be bigger than 1. Remember, it's just got to decrease after a certain point. So is that decreasing after some specific integer value? I think the answer is yes. So How do I show that for sure? Where's this negative? I mean, we could do a little sign chart, right? That'd be kind of annoying, though. I got a cubic function here. Ugh. I guess we could think about that. So let's just think about like a chart here and where this is. So it's 0 at 0, but I don't care about that, right? Where's the other place? The top of that is 0. Solve, right? Kyle is correct. Cube root of 2. So if that's 1, 2, cube root of 2 is like what? 1 something. So here's the cube root of 2. So if it's negative over here, we're good to go. You know what I'm saying? So f prime f. Let's stick in a test point like 2. If I stick in 2 to that, what do I get? 2 times negative 8 over positive thing is, yeah. That shows that f is decreasing after the cube root of 2, which satisfies what we need for the alternating series test because we've got the limit goes to 0 and it's decreasing for some n, some integer. So that means that this is a convergent series by alternating series test. Okay? Let's come back and look at another kind of different variety of divergence or convergence in the next spot.
Hi, Charles.
All right, so we just read page 934 and talked about the concept kind of conditional and absolute convergence. So I wrote it down in a little bit different way for your notes here. So if the absolute value converges, then you know for sure the original series converges. That's kind of crazy, but if you look at the proof in the book, I think it's definitely true. But I think this is my rephrase of their theorem. If you look at the absolute value and that series happens to diverge, the test kind of fails if you want to think about this as a test. The other thing still could converge. It's possibly conditionally convergent instead of absolutely convergent, okay? So I've got some classic mode weighting examples up on the board, so let's think about each one of these, right? We can use all the tools from before, but we can also use this new concept of types of convergence as well. So what do you guys think? What can we name this, by the way? We should be able to give this one a name. This is a solid one for, you should just recognize the name of it. It's the what harmonic series? This is the alternating harmonic series. Very good. So the alternating harmonic series, is it convergent? Is it absolutely convergent? Is it conditionally convergent? What?
Find out.
Well, what do you guys think? I think it's easy enough to where you can kind of just do all the stuff in your head. It's not like you have to write down a whole bunch. It's convergent. Okay. So that thing is convergent, right? So does that mean it's absolutely convergent, conditionally convergent, or what?
Well, we're going to take absolute value of it.
If you take the absolute value of it, will that converge? No, because the harmonic series is the most famous divergent series that people think, people without, just starting out think it's going to converge, but it doesn't. So if the absolute value doesn't converge, then it's not absolutely convergent. But John looked at it immediately, and probably several of you guys did too, and said, hey, alternating series test is going to work on that one, right? Because that is clearly going to limit to 0, and 1 over n is clearly going to decrease for all n. I mean, that's just kind of common sense, right? So the alternating series test says it does converge. So what do we call this then? Conditionally convergent. This is conditionally convergent. It's like the most classic conditionally convergent thing out there. Okay? So I think that should make sense to you guys. So absolute convergence is like a stronger kind of convergence. How about this one? What do you guys think about that one? If you take its absolute value and get rid of the alternator, is that going to converge, diverge, what? Diverge. Why, Ms. Bondino?
Because the factorial is a higher magnitude than the exponential.
Right? How would I write that out a little more formally, though? I'd say the
Order of magnitude. Infinity.
Now, if you want to explain that, you could say because. And you want to on the actual AP exam write things like this because they want justification. You wouldn't want to abbreviate on the AP exam just in case. I haven't looked up the latest thing on what they accept and what they don't accept, so don't abbreviate. You can on your homework. I should write this in there, but I'm being lazy. So that one's divergent. It's not conditionally convergent or absolutely convergent. Cool? Here we go. I guess you could even put the alternator back in here. That'd be a little better way to say it. Go like that. All right, so what about this one? What do we think? So it converges how? Absolutely, conditionally? Give me more.
If you take the absolute value and the t-series equals 1/2. Converges.
1/2, is that a convergent p-series?
I think so.
Doesn't p have to be more than 1 to be a convergent p-series?
So that's divergent.
So, if you take the absolute value, you get divergent series. Does that mean this is divergent? No. That's using the converse. Remember, the converse and the original of a statement are not the same thing. Before I erased that, I should have said that, right? The statement says, if absolute value converges, then regular thing converges. It does not say, if regular thing converges, then absolute value thing converges. That's the converse. That's not true. You can use the contrapositive, right? You can say, if the regular thing diverges, then the absolute value series will also diverge, but that's not a very useful fact. You know what I mean? The converse of that one's not very useful. So that means we've got to do something else with this bad boy. So it fails to be absolutely convergent, so we'll put that down. So we'll say, because of what Gabe said, absolutely convergent? No. It could still be conditionally convergent, though, if just the regular thing converges. So do what? Alternating. Take the limit. Yeah. We'll do it John's way this time, shall we? Less than that, right? We don't know. You can do this with the derivative too, just like last time. It's up to you. So that says this. Is that true? Yeah. How could you defend the fact that that's definitely true for all n greater than 1? I would say true by the growing nature of square root of x after n equals 1. Yeah, something like that. Okay, so that says by alternating series test, it converges. So we're going to classify this one as conditionally convergent, just like our very first one. Okay, so this one's also conditionally convergent. And I should write that out. I should say by the alternating series test it converges, so only a sub n converges, not the absolute value, so it's conditionally convergent. Is that good? Okay, good. We'll maybe look at one more today and then call it quits. Yeah, maybe two more. Have a look at this one. A little different, a little more interesting. So the question is, what is the first question you should ask yourself? Is that alternating? Exactly. This is just like the top of what you guys just read a second ago, right? We didn't talk about the top part. So is that alternating? Well, how are we going to find out? Yeah, we could try to do that. Very good. That's a great idea. Or we could just write some terms out and see if it's truly like alternating back and forth, or is it doing some other kind of pattern, right? So let's just plug in some terms. How about we just write out the first few partial sums? If I plug in 1, I get what? 2. So that's going to be negative, isn't it? Am I right? Over 3? Okay. If I plug in 2, I'm going to get 2 times 3 is 6 over 2 is cubed. Cubed is negative. I'll put plus in between. Over 9. If I put in 3, I'm going to have 4 times 3 is 12 over 2 is 6. It's positive. If I put in 4, I'm going to have 5 times 10 is positive. Is it alternating? The definition of alternating means switching every time. Is it switching every time? The answer is no. So could you do something like apply the alternating series test to it? No. But see, this issue of absolute convergence gives you a whole nother path to things that are kind of alternating but not quite. Because what happens if you take the absolute value? This top term, while sometimes it's negative, it's going negative, negative, positive, positive. I bet the next one is negative, negative. It's still kind of alternating. The absolute value, what's it going to do to that? Regardless of how the negative, positive thing switches, it's going to change them all to positive, right? So the absolute value of this is going to be the same thing as what? Which is, of course, this. Which is, of course, what? And is this one convergent? Yes. So this guy converges. Ooh, since it's geometric, we can even say what it converges to. By geometric series. So, or therefore, something like this. I like my triple dot, therefore. Therefore, absolutely convergent. So you might have looked at that originally and been like, oh man, it's not alternating. That doesn't mean it's not convergent in a really strong sense. This is a very strong convergent series. Okay. So a little bit counterintuitive perhaps, but not too much. All right, last one for today. You guys think, is that one absolutely convergent too? You guys think? This one's a little bit tricky. So, can we say it's at least conditionally convergent? I think you guys should be able to look at that and decide if it's at least conditionally convergent. Yes. By what?
By the alternating.
By alternating series, this is conditionally convergent. I'll write it out a little bit just so we can see the details. Now, because if you look at this guy, the limit as n approaches infinity of this, that's clearly 0, check. Is this thing decreasing? Well, we could look at it. I think it's going to be, isn't it? I mean, like, just think about it. Is this thing going to be decreasing with that part? Yeah. Here it is, though. Cross multiply. True or false? True. What could you put as a reason?
The growing logs grow.
Since trees, we want to be really flippant, we could put since trees grow, right? Okay. So this guy converges conditionally at least. Is it absolutely convergent though? Is it even stronger? Absolute convergence is a stronger form, so it's got conditional at least already. I think that's a little bit harder to say. Let's use a comparison test. Don't forget about your other tests, yeah? What could we compare this to? We could go 1 over natural log of n. I think that's going to converge as well. I think that's going to be inconclusive. Try comparing it to 1 over n, the harmonic series. I think if you end up comparing it to 1 over n, the absolute value, in other words, just this part, it's going to be bigger. So it's going to diverge when you look at that. So here's what I said. Should we do that comparison? Let's do it. I didn't do it. So directly compare. So let's directly compare with 1 over n. If we want to conclude anything, we know that this guy diverges, so we want to show that this guy is bigger, right? So is that true? Is that true? Order of magnitude, right? This is order of magnitude line. This is order of magnitude logarithm. Logarithms go slower than lines. You could argue it right there. Since that's true, which means since that diverges, this thing eventually is going to be bigger than it and also diverge. If you think about this with p-series, remember, go back to what Gabe said earlier about p-series. Remember we had that one that was like this? And we said that that diverged. Think about that compared to 1 over n, where it's clearly, the bottom is smaller, but it's getting bigger over time. And this is exactly the same situation. Okay? So, I think that's good. We're going to do one more example tomorrow, but you're pretty much set for everything. See you next time.
So
Hi,
it should be
Thomas.
conditionally